Good morning, good afternoon, good night to everyone, wherever in the world you are. Thank you for joining in here. We having a webinar today. Now, can you go to the next slide? The first and the important thing is you should now hear me. If you don't hear me, it's you and not us. Our sound works fine. Jonas can hear me. I can hear Jonas. So that audio works fine. So please check on your side if there's something wrong with the audio. And yeah, then we will continue from there. Otherwise, I'll show you a quick overview of the system. Can we go next slide? So what you have is a full screen of the presentation plus the webcams. Sorry, I'm a little bit struggling today. And on the right side, we have this control panel. And on the control panel, you see this red arrow button. With that red arrow button, you can hide and unhide this control panel. And if you look into that control panel a little bit more in detail, if you do that, Jonas, to the next slide. There we go. We see that we have the audio settings in the top where you can change the settings to whatever audio you want to have. We have the handouts, and in the handouts you will see today the presentation that we're going to go through. So you are able to download the presentation and look through that later on a little bit more, or do that while we are presenting here. And we have a question section, so you can send us questions whenever you want down there exactly. And if you have questions, send them over to us and we can answer these questions. This time, the way we're gonna handle the question is that we're gonna sum up all the questions towards the end. So I will try not to interrupt Jonas during the main part of the webinar, but then in the end of the webinar, we will run through the questions, at least as many questions as we can. Whatever question we're gonna miss, we will answer you later on in an email. But we hope to go through many questions. Try to send the question as soon as possible. So the later you send the question, the more likely is that we will not get to that question afterwards. Okay, so first of all, my name is Christian Born. I'm here the host of the webinar. I'm gonna guide you a little bit through that stuff and make sure that everything is running smooth. I am not running the presentation itself. We have a what was brown belt jiu-jitsu master here.
Good morning, everyone.
Good morning, Jonas. He's bench pressing 100 kilos, deadlifting 200 kilos, so don't mess with him. And I don't know, maybe you want to talk a little bit about yourself, Jonas, quickly. Tell what you're doing.
So more relevant to my background in Comsys, I'm the co-founder of the company and I'm the CTO. My main degree is actually in software engineering. So for me, the software has a special place. I think that's what powers our system, and yeah, I would love to talk about it.
Exactly. Excellent. And Jonas, I would say I'll give everything over to you, and you can tell us what you're going to present here today, what you're gonna talk, and I'll just hide away for now, let you run the show, and just interrupt you if something urgent comes up. Otherwise, we see you later at the questions.
Okay. Thank you, Christian. So today we are going to talk about release 2.2 of the SEC2 software. It's a very important release for us because we believe that with the same hardware that you might already have, you will be able to solve much more actual problems using the same hardware or even using less hardware than you would need before. There is a lot of active filters on the market. And of course, one of the key differentiators is the software. How can I apply the system to solve an actual problem? No matter if it's electrical vehicle charging, if it's a data center, if it's a variable speed drive, if it's EC fans, whatever the load, there is a much bigger chance or much bigger opportunity to actually solve the problem of the customer, or utilize the grid better, or whatever the goal is of the installation, using software 2.2. And this is kind of the theme, to either make it possible to solve a problem that you could not solve before, or to make it usable in more applications, or to simplify configuration, simplify commissioning. And then there is a hidden theme that's maybe not so apparent from this presentation, is that it's a preparation for future hardware platforms. So some of the bits and pieces that we have introduced in this software are preparing us for future hardware. Some of it is very visible, I will talk about it later, and some of it is simply a preparation for the next generation active filters that will come from ComSys. So the detailed agenda looks like this. This is all the major topics we're going to talk about. There are a myriad of smaller fixes in software 2.2 as well, that we are not going to mention so much, but these are the major features. So we have the ability to auto-tune the system, so it can actually set its harmonic parameters by itself. We can indicate total demand distortion, which is important for a number of customers. We have something called multi-master node masking, which allows us to apply multi-master solutions in scenarios where we could not do it before. We can mix and match compensation settings, so that actually we have a different kind of compensation on different harmonics. I will explain what it means later. Also, we will revisit impedance control. Some of you who are maybe long-term partners of ComSys have been in touch with impedance control. Maybe you have used a P200 system. So the big news is that for software 2.2, impedance control is an official, fully supported feature. It's not a technical preview anymore. We have an enhanced parallel system support, allowing you to use multiple parallel ADF systems in new ways that was not possible before. And then we have a host of web user interface improvements. At the end of all this, if I don't talk too long, we will have time for a summary and a Q&A. So let's jump right into it. Auto tuning, I think, is a good first topic of 2.2 to discuss, because it's something that is easy to explain, and it makes the system easy to use. So right now, we have the ability to auto-tune according to IEEE 519. And as you might know, to be able to do that, to make sure that you fulfill the requirements of IEEE 519, you must have a demand current. You must have the demand current defined to be able to know that you reach the goal. I will explain what it means in a minute. So this means that the demand current is a value that you have to set in the configuration. And unless you don't set this value, the auto-tune option will not show up in the compensation dialog. This is our first attempt of auto-tuning system. It means that before you had to, I will quickly switch to a system I have running here. Before, when you go into the compensation, you have to write those numbers manually. Maybe you want 50 here, and maybe you want 50, and so on. And what happens is that if I enter a TDD value, I set it to 200, and I save it. Now when I go to the compensation, I now have the option to do the auto-tuning here. I can click this, and I can click auto-tune, and the system will actually tune itself. Right now, we only allow IEEE 519 tuning. Future versions of the software will allow tuning to additional standards or additional regulations. So the auto-tuning takes all the relevant parameters into account. We are looking at the voltage harmonics, the current harmonics, the individual harmonic limits, and the TDD and THD limits. So for example, you might have a grid where you have a short circuit ratio between 50 and 100, And this means that you allow maximum 10% of the demand current at harmonics from 3rd to 11th, and so forth. There is also a voltage distortion requirement, which we also take into account. And when you enable auto-tuning and when you run it, the system will attempt to tune the system in the most efficient manner possible, meaning giving you most bang for the buck. So let's take an example. Maybe you're concerned with a higher harmonic, with something like this. And if you tune it manually, maybe you put a too high number on the parameter. So you're using more power from the system than you actually need to meet the required goal. Now, the algorithm is written in a way so it tries to first apply the numbers or the settings where it has the largest effect of the outcome. So it tries to be as economical as possible with the available output current of the system. Only drawback of this is, of course, that when you do the auto-tuning, you need to have a high load. You need to have a situation which is similar to or maybe equivalent to the worst case scenario. But if you have that, you can just click the auto-tune button and the system will actually tune itself. And when we enable the TDD, we actually see now that in here, we can see the TDD number as well. And even if you're not using auto-tuning, this is a very important feature because it's common that the customer asks you, maybe I need 5% THDI, or maybe I need 10% THDI. And this is not a very useful number, because if you have a very low load, maybe you have a demand current of 200 amp, but the system is running, not the ADF, the load is running in a low load scenario. Maybe you have 20 amps or 10 amps at the time being. You might have a distortion of 70% on the current distortion without damaging the grid, because the voltage distortion is also very low. And this is why demand current is so important to understand, and also so important to actually show in the dialog box here. So what I showed you just before is that to set the demand current, you need to input a value here. And actually I did it in here. You can now see that here we have the TDD as a value. This system is idle, so nothing is happening. Now I go back here and I disable the demand current. I put it to 0 again. I click save. And when I refresh the page, you see that the THDI is now 40% or 20%, depending on which phase we're looking at. And this is because we have a low load scenario. So basically we have just 1 amp or 2 amps of load, but the THDI is very high. And this illustrates why THDI is really a bad measure for the customer to indicate that we have a problem. Simply by enabling the demand current, now maybe we have a 100 amp feeder instead. We wait a bit and we see that it changes to TDD, and now we have a distortion of 0.5%, which is obviously not a problem. So even if you don't use auto-tuning, we really strongly recommend that you enable TDD when the customer has a current distortion goal, because the TDD value will show you a realistic value that is actually indicating what is going on, and it's indicating how much is the current distortion load of my system. And TDD is defined like this. If maybe I should have started explaining that. So we have the harmonic RMS current, which is defined as the square root sum of each of the individual harmonics, and we divide it by demand current. And during full load, meaning that if we have a demand current of 200 amps, that basically means that the average maximum current that we will see in the system, in the electrical load during a long time, is the same as the full load. Then THDI and TDD is the same number. So during full load situations, TDD and THDI will actually show the same number. But if we have a low load situation, then TDD is a much better measurement that is actually indicating the harmonic loading that you have. So this was a nice short introduction to what we can do with 2.2. We see that a couple of customers has already started using auto-tuning in the field with good results. So I encourage our partners to try it and tell us what you think. And now let's go to a slightly more complicated topic, which is also something that has been cooking for a while. So we're introducing now the multi-master node masking. And a multi-master configuration is usable when you have a system with several ADFs that are on the same bus. And right now we have an example on the right. We have 2 generators. We have a large single bus that is dividable with a bus tie. So in normal operation, you're running one of the 2 generators. The bus tie is closed, so basically you have one large electrical grid. And then you have your loads, you have VFDs on the left side and on the right side of the bus tie. In this case, it's tempting to just connect all the 4 systems and you do multi-master. So you're configuring node 0 and all the compensation settings will automatically be distributed to node 1, node 2, and node 3. If I take node 0 down for service or for maintenance, node 1 will take over and control the system and it works seamlessly. You get the redundancy that you need to run the system. However, if we have situations where the bus tie is opening, it means that if node 0 is now controlling all the ADFs, it cannot see the load on this side of the bus because it has been isolated. So prior to version 2.2 of the software, multi-master would not work properly in this situation. And this is unfortunate, especially for marine applications, because it's very important to be able to run several ADFs with the bus tie closed or with the bus tie open, depending on the operation mode of the vessel. And of course, also in other situations where you have redundant grids, you would need the same functionality. So what we can do now is we can configure the multi-master to respect a primary and secondary compensation set. So what it means is that here I can say that I have 4 nodes on the bus. I'm configuring the system so I have node 0, 1, 2, 3, like in the example before. And then I can configure it so that in the primary nodes, in the primary compensation set, my node is seeing 0, 1, 2, 3. And in the secondary set, it's only seeing 0 and 1. And what that means is that when the bus tie is closed, we only have one large bus. All the ADFs are working together. However, for the systems who get the secondary node 0 and node 1 in secondary compensation mode, it means that when the bus tie is opening, we need to send a signal to the system via Modbus or via digital input. And then those 2 systems will be working together. We will have a similar configuration so that node 2 and 3 are only seeing node 2 and 3 during the secondary compensation set, actually meaning that node 2 will now be the master on the right and node 0 will be the master on the left. So this is kind of a multi-master application. And the typical use case for this is to allow you to run either on a marine vessel or in a system where you have some kind of emergency power, where you need to maybe normally have the bus tie open or normally have the bus tie closed, and you have a secondary compensation set depending on the position of the breaker. And it shows like this. So when you pull this down, you can just click in and click out the nodes that you want to be visible. Now this means that you have to do this configuration for every ADF. So if you have the compensation settings, all of them are running in Multimaster. You know that the compensation settings are automatically propagating between the systems. But the network setup, how one system is talking to the other systems, you need to manually set on each of the systems. Again, doing this, in the secondary set, it's always, no matter if it's secondary or primary set, it's always the node on the bus with the lowest number that is the master at the time. So let's explain that example. We go back to the system, we have a primary setting, and then the node mask is 0, 1, 2, 3 and 0, 1, 2, 3 for all the systems. It means that all the systems are talking to each other when the bus tie is closed. When we open the bus tie, we have the secondary setting, then system 0 and 1 will see system 0 and 1, and system 2 and 3 will only see system 2 and 3. And basically, it means that node number 0 is the master on the left side of the bus, and node number 2 is the master on the right side of the bus. And this transition is seamless. This works on the fly. So as long as they get the signal to split the bus tie, they will separate immediately. And if you take one of the systems down, then of course, if the bus tie is open, this one will be the master. If the bus tie is closed, this one will be the master, or the one with the lowest ID. So this is an expansion of the multi-master concept, allowing you to run multi-master in a new host of applications, especially in marine environments. This is very valuable. And there is a twist to it that we will come back to later in the presentation. Another thing we have implemented is the ability to mix compensation. We now have the ability to have each harmonic define a separate compensation type. So you can't have several compensation types on the same harmonic, but you could have, for example, you want to combat current harmonics. So you have IEEE 519 as a required standard. It means that you're concerned with the current harmonics. You need to keep the current harmonics down to comply with the regulation. But maybe a resonance show up in the system. So on the 17th harmonic, in some conditions, you get a resonance, and you want to combat that resonance. And maybe the current harmonics isn't that bad at that harmonic. Now, what you can do is you can pull down the harmonic mode override, and then you can go into the 17th harmonic and select a different compensation type. I will show you how it works. So we go into the compensation set, and right now you can see we're editing the harmonic set point, and we have CT control enabled. So maybe we have 70% here, maybe we have 50% here, maybe actually we have numbers set by the auto-tuning algorithm. Now I can select what I'm editing. So I will instead select the harmonic mode override. And now I can go to the 17th, was what I said, and I can enable impedance control. I can go back to the harmonic set point. Now you should see the text here, it says impedance. And I can enable that I now run 30% of impedance control. It means on 5th and 7th harmonic, we're running current control, and on 17th harmonic, we're running impedance control. And I don't have to do that as an example. I can also take sensorless control. So I can mix sensorless, impedance control, and sensorless and current control in the same setting. Obviously, we can't mix open loop and closed loop compensation because that's determined by the hardware. What you can see here also is that if we go into the override, we have some confusing options. CT control seems to be easy to understand. Sensorless control, impedance control also. But now it says CT plus U, and it says default plus U. And this simply means default is the major mode I selected. So, okay, I said I want to have CT control here. It means I get CT control everywhere as default. Default plus U means I get unbalance enabled, or just default means I have unbalance disabled. So it gives you a very, very fine-grained control of what is going on. And by doing this and having this ability, it's absolutely invaluable if you are running current control, you have a conventional setup, and then you get a problem with a resonance that you didn't expect. Maybe there was a system simulation done prior to the installation of the active filter, and then you didn't anticipate the resonance at the frequency where it showed up, or you made a retrofit, you quickly shipped a system, and you didn't do a system study, and you weren't prepared for the resonance. Now you have the tools to immediately solve it on site. And with impedance control, maybe you don't need to add an ADF P200 to make it work. So this is a toolbox that allows you to immediately solve problems on site without adding extra hardware. It adds a new degree of configurability, but it also allows you to mix and match. Maybe you want to have the 7th and the 5th harmonic low because you want to limit the current of the feeder. But on the higher harmonics, you might be more concerned with the voltage harmonics. So maybe you're running current control on 5 and 7, and 11, 13, 17, 19, 23, 25, you're using some kind of sensorless control, either sensorless control or impedance control. And I kind of know what you're wondering right now. Because I said, when you get a resonance, maybe we should enable impedance control. So let's talk about impedance control. Historically, we had 3 modes of operating the ADF. Historically, we really only had 1. I'm sorry. So we had current control in the past. This was the only option. We observe the current, we calculate a correction, and we inject the correction current. Now, sensorless control allows us to do the same, but we're just observing the voltage. So it works like this. We're looking at the voltage. We see that, okay, we have a high distortion of the 7th harmonic, for example. We're now calculating, okay, how to get the 7th harmonic voltage to 0. We need to inject this current. And basically, when you're writing 70% in the setup, let me show you. When I'm saying here, I'm saying a percentage number for sensorless. It means we're limiting the output of the system to 30% of the maximum allowed output current at that harmonic. The goal is always 0 in sensorless control. So this allowed us to do the same, but we now can do it without a CT, or we can use it to control background distortion, which is a very important application for some customers. However, the problem can be that we have a high system impedance, and this is what is causing a resonance. A resonance is literally, the definition of a resonance is that you have a capacitance and inductance combined so that you get a very high impedance magnitude at a certain frequency. And maybe you have a load that is exciting this, causing a high voltage harmonic, causing trouble. So our approach to this has been to use the ADF P200. And what we have brought to the table now is that you have impedance control available for all systems. And it has a similar application. It allows you to insert an impedance to the grid. And it allows you to do it using a P25, a P100, or a P300. And you can have a P200-like behavior. So the curve here is the settings curve for a P200 system. And basically what you're defining as the user in a P200 is the impedance you insert to the grid. And here we have chosen a slightly higher impedance at this frequency, meaning we have less interaction. And here and in the higher frequencies, we have a very low impedance, giving a very strong interaction with the grid, giving a very strong damping of, for example, a resonance. It's still like this. The P200 is still the fastest control type we have. So if you need a very, very fast response, or you have a very nasty resonance, you would still need the P200. But in most cases, a regular system will be good, like an ADF P300. And especially if you need a high power density, you need lots of power, then the P300 is the best with impedance control. And another big thing with this is that using the P200 is hard, because defining this curve is tricky, because you're manually editing the biquads in the control. And it means that you need to have some system knowledge, you need to understand a little bit of control theory, or you need to have a good sense of what is going on in the system, like a good feeling. Now, with impedance control in P100, P300, P25, it's much simpler. You simply enable impedance control. You saw before that we could simply do like this, and then you put in a set point for the numbers that you want. So this is more like you have already been using a regular control. The control interface is the same as CT and sensorless control. 100% now in impedance control corresponds to the minimum allowed impedance per module at the selected frequency. So it means if I input 70% here at the fifth harmonic, the system will actually only interact with the fifth harmonic. It's not wideband compensation as the P200, which is a major advantage. Now you know that you have been sensorless control has been available for quite some time. Since software 2.1.2, it has actually been a technical preview, and quite a lot of our partners have been using it in various applications. But since 2.2, this is now officially released. And of course, when you get more options, we now have impedance control, sensorless control, CT control. The big question, or the obvious question, is when do I need to use it? When do I need to enable it? Well, if you have a resonance in the system, you might be forced to use it because you can't combat the resonance effectively with, for example, current control. It's also very good if you have a voltage control application and you have a power-hungry low order harmonic that you need to combat. For example, on a marine vessel where you want to take down the fifth and seventh, or you have a generator application or something like that. Another obvious application is that, again, like I was talking about before, you install a system, you need to fix a problem that's out there, and you don't want to bring a P200. You already have a system on site. Then you can simply add a license key, you can enable impedance control, and you can hopefully combat the resonance. Another thing where you can use it is that you want to actively control the impedance of the grid. For example, when you are switching from a transformer to a generator, you can use impedance control to actually lower the impedance on the grid and to make the grid with a generator behave more like a grid with a transformer. And of course, you can combine it with other control types. Now, adding to the power of being able to combine various modes of operation, we have significantly enhanced the parallel system support. So historically, we were able to run open loop current control with or without multimaster. And we were able to run closed loop current control with multimaster. Starting with 2.2, you're now also able to run impedance control in parallel systems, and you can do it with or without multimaster. And you're also able to use sensorless control using multimaster. And what it means when I enable impedance control when I enable multimaster for impedance control is that it's actually just propagating the settings. Impedance control by itself is implemented in a way that the systems will not start to compete. And we're doing that with a control trick that it's unfortunately not possible to do in sensorless or in current control in the same way. But it allows you to have parallel system with basically zero configuration. You simply just enable the harmonics you need on every system on the bus, and then you go. And we had a convoluted example previous in the presentation with the split bus. I will actually jump back to the slide. And here we had a lot of settings to do with enabling the secondary and the primary compensation set to be able to define how is this system seeing the other systems when it's working. With impedance control, you don't have to do that. You can simply just enable the harmonics you need on every system and just go. So this means you can run impedance control in parallel systems. You can run impedance control mixed with other control types on the same system. And you can run multi-master with impedance control, or you can run impedance control without multi-master. So the EDF as a power quality toolbox is really now, the flexibility of the system is simply unprecedented. You can now combine all the control types. You can combine them in the same systems. You can combine it over several systems. And what it means is, of course, when sizing a system prior to the installation, you have more flexibility to design a system that will fit your need. But maybe more importantly, when you're standing there on site, you're commissioning your system, you're trying to get it work, you have some unforeseen issue, you have a much improved possibility to correct a previously unknown problem with the tools that you now have in the toolbox available. For example, resonance detected, you can add impedance control. Sensorless systems run out of power. Now you can have parallel sensorless systems because it now works in multi-master, and you can combine control types. And I'm writing an example. I'm writing here more examples, question mark, because I'm sure that you, our partners and customers, you will find new applications to utilize this that we didn't think about. So this was two quite heavy theoretical topics, and we will now switch over to talking about some simpler things that are hopefully, I will not lose the audience as easily here. We have some web user interface improvements, and one of the first ones is that we have a limitation indication. Now it means you're running the fifth harmonic. Here it says that we have a limitation active. This doesn't mean we have a problem. This simply means that we have a limitation of one of the harmonics. And if you make a mouse over here, you can see that it's compensating at reduced output due to harmonic limitation. So what it means is that maybe you're on site, you have commissioned your system, you don't know, why am I not getting more power out of the system? Or maybe you were expecting to have kind of a different result. Now, when you're running at maximum power, you will see that the fifth harmonic is actually limited. And you will get the feedback that, okay, if I need more compensation of the fifth harmonic, maybe I need to add more systems to the mix. So it's just a way for the system to indicate what is going on. Also, when we have the global limitation, like the total output power is limited, you will have the message limitation active appear. In future versions, by the way, we'll change this warning triangle, because that sounds like a warning to an information sign, because it's really not that something is wrong, it's just an informational alert. And here you can see that the RMS factor is 94.55%. And basically what this means is that with the settings we have in the system, we're only able to give 94.55% of what the control is asking for. So this is also a way to get feedback that, okay, I have a 1000 amp drive, I'm using a 300 amp filter, but maybe I would need 320 amps to totally compensate what I'm seeing. And you will get a clear indication what is going on. And also it's very detailed, because you can see the RMS factor, you can see the peak factor, the overmodulation factor and the temperature factor. So you will know exactly what kind of limitation is actually limiting the output power of the system. And let me also add that if you're running with an undersized filter, meaning that you have a very large drive system, maybe you have 16% of voltage harmonics prior to compensation, maybe you just want to bring it down to 7%. It means that you're undersizing the filter on purpose because you want to not have a too big installation. You just want to reach the voltage harmonics goal. Then you will always see the RMS factor because there will always be more current to remove on the grid. But you don't need to, because you don't need to go further than reaching your voltage harmonic target. Another nice indication that will help many of our partners significantly is now that we're able to indicate time to service. We have the time to service shown in the about dialog. I think I have it visible down here in the system. No, I do not, because it's not enabled there. So you have a specific login. The customer cannot access this, only the service partner can access it. Here you put in your company, your contact, telephone, email, and you put in the service interval. And it works like this, that the system is actually not counting days, it's counting runtime. So if the service interval is 100 days, but you're only running the system every other day, like you shut it down every other day for some reason, it will actually take 200 calendar days until the 100 runtime days have been achieved. So this also means that we're internally measuring how long time has the fan been running and that kind of information. And we will use that to give more detailed information in future releases of this software. Another improvement is that we now have built-in support for HMI4, which will look somehow like this. This is obviously a mock-up. And we have a dedicated hardware route and software route to allow communication with the HMI4, which is actually a pretty sophisticated solution. HMI4 by itself will have an integrated web browser running on a dedicated computer platform that will talk to the main system, and implementing support for this was actually a major undertaking. The upside is that we will now allow applications to be run in the future on the HMI4 that will provide additional functionality than what you just have in the core system. Another, in my opinion, very nice and important improvement is that we now have the ability to swap and invert CTs. I know that we had an ADF Academy the last few days, and maybe it was mentioned that one of the most common problems on site is that the CT is wrongly installed. And now you can fix it in software. First of all, you can invert any CT individually. So if you just need to swap the polarity of CT on phase 2, you can do that. You can also swap the position of the CTs. So the input phase 1 is actually mapped to phase 2, and phase 2 is mapped to phase 1. So it allows you to correct the installation without opening the cabinet or without physically moving the CTs, as long as you have one CT on each bus bar or on each face of the cables. You will be able to correct it in software. We're not able to, however, correct if you have two CTs that are 200 to 5 and one CT that is 500 to 5. That's not possible at the time being. But the common installation errors you can now fix simply by swapping them in software. And I think it will save you a lot of time. So finally, I have a brief summary here before we go into the Q&A. So software 2.2 brings, first of all, simplified commissioning. You can swap the faces of the CTs, you can invert the CTs, you have the auto tuning that will, you have the TDD that makes it much easier to see what's going on. You have the indication in the user interface that allows you to see what is going on under the hood a little bit better than you could before. And then, of course, you have the increased flexibility of compensation. And I think this is really the big news. You can mix and match harmonics. You can have both impedance control, sensorless, current control running on the same system for various frequencies. You get an improved service support with the service indicator, and you get a significantly improved support of functionality for parallel systems with the ability to run all compensation modes in multi-master, which you could not do before. And of course, impedance control is now officially launched. So in total, or the big picture, at least from my point of view, is that you're now able to run ADFs in a vast number of applications that you could not before, and you can fix a big class of problems that you were not able to fix before. So that was the presentation. We're now going to jump over to the Q&A. I'm looking at Christian, who is across the hall here.
Yes. Hello. Yes, we have a few questions that came in. Keep them coming. We have still a bit time for questions, so we will just bring up one after the other and then see if we have something left in the end. So on the auto tuning, let's start over there. We got some question on the auto tuning. So the compensation settings set by the auto tuning, are they fixed or are they dynamically changing with the load?
So they are fixed. It means that the system is trying to tune according to some kind of worst case scenario, that you're running the load, you're trying to get to a full load situation, you're tuning the system, and it will then make a fixed set of parameters. And this is kind of the same that you had before, because when you tune the system manually, you also get a fixed tuning. However, we have added support that the auto tuning function can actually be triggered. So technically speaking, we have the possibility in the software to add functionality in the future where you have a completely dynamic tuning that could run all the time. But for this release, it's a fixed tuning. I would also like to mention that when you have done the tuning, when the system is done, you will actually see the result. So if you want to use the auto tuning as a good starting point and then manually tweak it, you can also do that.
Excellent. So you're making an auto tune and then you get the settings and then you can adjust that a little bit.
Correct.
So I got one quite interesting idea in here from a customer. They were asking, hey, if we only have the IEEE 519, but we are doing both the voltage and the current, can't we just set up the short circuit ratio of 2000 and run the IEEE auto tuning and get a nice result for 8% voltage overall and 5% single order harmonic?
Yes, you can, and you can also set the demand current to a high value, or you can set the demand current and the short circuit ratio. Let me show you the slide. Because you can both control the demand current and the short circuit ratio. Now, if you set 20, then of course it will try to make a very strict limitation of the current harmonics. So if you go the other way around, you set 1000, or if you set a big demand current, it will mostly focus on the voltage harmonics.
Awesome.
And in the example system I had, maybe you noticed, I mean, here we have basically zero distortion where we're not doing anything. So if I run the auto tuning here, it simply does nothing because it doesn't need to do anything.
Correct. Awesome. Perfect. So then we have the next question in the auto tuning. Do you need to set up mixed control compensation before performing the auto tuning, or will the auto tune sort out the mixed compensation as well if that is needed?
I would run the auto tuning for the current control first, and then I would modify to the mixed control type you would want after that.
So it's the auto tune is not saying directly, okay, here we need to we need to adjust impedance control here.
Correct.
Okay, awesome. So then we have some questions on the multi-master node masking. And I think there is directly quite of a little bit confusion in there. So the first question, does the multi-master node masking feature eliminate the need of summation transformer between the CTs?
No, so it does not. So basically the node masking is only controlling who, if I'm node 0, who am I talking to? Am I talking to node 1 or node 2 or node 3 or all of them or just a subset? The information node 0, if that one is the master, is using to compensate still comes from the CT or from the voltage if it's a sensorless application. So if you have current control, the requirement of summation CTs or CT setup in general is the same as it was before. However, if you have a problem with that, of course, you now have the ability to use sensorless control with multimaster, or you can use impedance control, and you don't even have to use multimaster. So now you have much more options to actually get rid of the CTs if they are a problem. And I know they can be very hard to practically install. And of course, also with reference to the inversion of polarity and the swapping of the individual CTs, of course, if you did mess up the summation CD setup, then you're kind of smoked, and you have to go back in and fix it, because we can't do that in software.
Yes, so with that we can actually kind of also answer the next question that was like, they said a nice feature, but is it useful in CT control, or is it mainly useful in sensorless control? And I think we can answer that it can be useful in CT control, but it is a main feature for sensorless control.
Correct.
Excellent. Good. And then we have a very relevant question here. How does the ADF know if the bus tie is open or closed?
Correct. And let me just start by saying that there are no stupid questions, so all questions are good questions. The bus tie, the ADF cannot magically know, of course. So either we need to have a digital input fed to the ADF telling it to, now you have to be primary compensation, or now you have to be secondary compensation. And you can set this up here. No, wrong place. And then you can select this one. The other way, which I recommend, is to actually enable Modbus TCP and have your PLC or whatever is the overarching control system actually tell the system what mode to run, because that's the safest and most scalable approach. Using the digital inputs is a bit more error prone. I mean, you can do it, but I prefer to actually use the Modbus.
And maybe we should actually mention here as well, one feature that you didn't talk about here was that the Modbus TCP is now available for everyone without license key in the newer software.
Right, correct.
Perfect. So impedance control, we have a little bit more questions here. So with impedance control enabled, is it necessary to consider the changes of the fault current calculations on the network? Can the P300 contribute significant to the fault current?
No, it cannot. And there are several reasons for that. The first is that the ADF is controlling its output current. So it means that if you have a motor that acts as a load and the motor is spinning and you have a short circuit, then even when the voltage goes to zero, of course, the motor will keep spinning and it will feed power to the grid. And you use this rule of thumb that 6 or 7 times the nominal current is actually a contribution to the fault current. And those currents can be very significant. The ADF is an inverter, so it's controlled by software. It has a peak current limitation, it has fuses, it has a runtime control limitation, and it will try to limit the damage when it sees that the current is rushing. It will open the contactor, it will disable the switching, and one of these mechanisms will come first and simply stop the output current. The other reason is that the fault current is predominantly on the fundamental, and impedance control is a harmonic, meaning that yes, we are lowering the impedance on the harmonic. But consider, for example, if you have the 17th harmonic and you have a grid that is purely inductive, it means that on the 17th harmonic, the grid impedance is 17 times higher than on fundamental. But in this case, we do not have a resonance. So this is not really interesting for us. Now we're adding capacitance to the grid, and maybe now on the 17th harmonic, the impedance is further a factor of 10 times increased, meaning that maybe we have 170 times more impedance on the 17th than we had on the fundamental. And this is what we want to work with impedance control in the ADF. We want to lower this 170 to something more nice, maybe 20 or 10 or 5 or something. But we will still have much more impedance than we have on the grid. Now, some of you will ask, okay, if I have a really large amount of ADFs, like if I have 15 ADFs, and then I have a generator that is pretty weak, couldn't the short circuit power of the ADF be bigger than of the generator? Yes, it can. This is true. And we would be happy to sell you the ADFs, but you don't really need it. So it's a kind of a theoretical thing that will never happen.
But overall, we can say, I mean, we're changing the impedance, but we're mainly changing the impedance on the frequencies, on the higher frequencies, on the harmonics, and that is not responsible for the short circuit.
Correct.
We need to be a little bit quicker here right now, so I jump over a few questions. I'll just try to get some basic ones. Whatever questions we're not gonna answer now, we're gonna answer later on in an email. So we have all your questions here, so don't be worried about that. License key. Do we need an extra license key for the impedance control?
Yes, but it's all actually packaged in the same license key as for sensorless control. So it's the same. If you get the license for sensorless, you have the ability to run all control types.
Awesome, perfect. On the service indicator, we got a question. Will the warning be shown on the HMI as well?
Good question. I think we have to answer that in the email.
I think it is a yes, but I'm also not 100% sure.
Exactly what I think.
And then there's a question, how to judge whether CT installation is correct when CT is in open loop? And I think doesn't make a difference.
Well, it kind of does, because no, it doesn't really. No, you can see my screen. So
yes,
here we have, the CT current. So basically it's very, very low. You can't see anything. And if you look at the phasor diagram, you see that, this looks horrible. Although they are pointing in just any direction they want to point. So this looks wrong, but it isn't. So if we start add current, I can't do that right now, I'm sorry. But if I would add current here, if I would start a load on this grid where this ADF is installed, because this is actually a physical ADF, you would see that those would sort themselves. So the advice is, if you have an open loop installation, enable the load, but don't enable the ADF. Just take a look at the phasor diagram and see if it makes sense. You have to keep in mind is the load inductive or capacitive, and then you can figure it out by looking at the phasor diagram if the installation is correct.
And I think it's both the same for open loop and closed loop.
Correct.
Then I have some general questions. So one question is, we got a new user manual. Are all of these features explained in the user manual?
Yes, everything is explained except for one. There is a new user manual coming, and what is not properly explained, that was left out because it was added very late in the process, is the limitation. This one is not properly explained in the manual, but
Okay.
there is a revision of the manual undergoing right now, and we will add this, and then everything is explained in the manual.
Awesome. And then a question that I don't know if you can answer that actually right now. Where can we download the software 2.2 and how to install it?
Well, I'm looking at you, Christian.
Okay, so you can download it if you have partner web access. You can download it from our partner web. Otherwise, talk with whoever sold you the active filter. They will be able to give you that software. And installing the software, I mean, Jonas, you can show that quickly. It's very easy. You just open the web interface. You
Scroll
go to
down
the
here.
about.
You click the upload firmware.
Exactly, and you select the firmware that you want to install.
Oh, actually, I have a firmware here. Looky.
Awesome. So we click on that, load it in, and then it updates the software.
Exactly.
It uploads and then updates the software.
Exactly.
So that is a very, very easy process. So we are actually out of time. I have maybe like 10 more questions that came in. I'm not able to answer them, or we're not able to answer them right now, but we're gonna answer them later in an email, hopefully today, latest tomorrow, I would say. And yeah, I would say thank you, Jonas, so much for presenting everything here.
Thank
Any
you for
last
listening
words?
in. Thanks a lot.
Awesome. Thank you. Thanks everyone for joining in, and I hope you enjoyed it. And we see you guys next time for the next webinar, whatever we have, or we see you in person someday, hopefully. Thank you.